Hello, and welcome to my walkthrough of a question involving a charged particle moving through electric and magnetic fields. Let's have a look at the question. A point particle with mass m and charge q is subjected to a constant and uniform magnetic field, B equals Bz, and an electric field, E equals Ex. Determine the motion, i.e. the position as a function of time, rt, of the particle, assuming that it starts at time t equals 0 at the coordinate origin, r0 equals 0, with vanishing initial velocity, v0 equals 0. First thing we can do is make a little diagram of our system. So here we have our point particle with mass m and charge q, and we can make a coordinate system and place our magnetic field in the z direction and our electric field in the x direction. Now, the equation that describes the motion of charged particles through these fields is called the Lorentz force, and it's given by this equation. And we can write out our individual pieces of this equation, as we know that Q is just simply plus Q. Our electric field is our electric field in just the x direction and 0 in the y and z direction. Our velocity is our velocity in the x, y, and z direction. Our magnetic field is our magnetic field in simply the z direction and 0 in the x and y. And force equals mass times acceleration as Newton's second law. But we can rewrite our acceleration as the change in velocity over time, or as I like to say, v dot, which is much easier to write and saves us time with the fractions. Now, first thing we need to do to solve for the Lorentz force is to find v cross b. Now, v cross b can be very simply given as this cross product here, which expands out to these sub-matrices of the components. And you'll notice that for k, you have two zeros on the bottom, so your determinant will simply be vx times by 0 minus vy times by 0, so it cancels out. But I and j do have components, and these are written as vy dot b minus vz dot 0, and minus j vx dot b minus vz dot 0, which simplify, oh, you've also got your 0k, and these simplify to be vy dot bi minus vx dot bj and 0k. So here we have our solution for v cross b, and we're going to put that to the side and use that later. Now what we would like to do is we would like to find our force vector components in x, y, and z. Now we can do this by taking our equation from above of m v dot, and remembering that we have vx dot, vy dot, and vz dot, we can equate them to our Lorentz force as we have just found v cross b. So in our x component, we have QE plus VYB, as these are our x components for our electric field and our x components for v cross b. In our y, which simplifies to QE plus QVYB, this is just timesing in the Q. Now in our y, we have Q0 minus VXB, as our electric field in the y direction is 0, and our component in y for v cross b is minus VXB, and this simplifies to minus QVXB. And in our z, we have 0 components for our electric field and 0 components for our v cross b, so the solution there is simply 0. Now that we've found that the z direction of the force component is 0, we can actually solve for vz. Now this is our equation here, m v dot z equals 0, and if we integrate on both sides with respect to time, we get m vz equals a constant. Now since our initial velocity is 0, we can say that c equals 0, and therefore vz also equals 0. Here above we have our force components in the x, y, and z, and we also have vz equals 0. But in order for us to find vx and vy, we're going to have to solve some differential equations. So here is our first equation. mv dot x equals qe plus qvyb, and v dot y times by m equals minus qvxb. Now, if we take the time derivative of our first equation, as we see here, we get mv dot x and qv dot yb. Now, the qe is constant with time, so it disappears, and the v is the only thing that changes with time, so that's the only thing that gets a dot above it. Now, you'll notice from our second equation that if we rearrange it slightly, we get v dot y equals minus qvxb over m. And we can substitute this into our equation below. And if we put our q into the bracket and our b into the bracket and divide by m from the front, we get v dot x equals minus q squared vx b squared over m squared. So here we have a double derivative, time derivative of v on one side and a constant with vx on the other side. This is a harmonic oscillator, and we know how to solve harmonic oscillators. What we have here is a second order differential equation, and the second order differential equation solution looks of the form Vx equals alpha cos omega t plus phi. Now, if we take the double time derivative of this, our omega comes out to the front and gets minused, but our cos stays the same. And you'll notice that alpha cos omega t plus phi looks exactly like our Vx that we had at the front. So v dot x equals minus omega squared Vx, which is exactly what we have above, and comparing the two equations, we see that omega equals qb over m. Now, if we look at our second equation, we can rearrange this to find v dot y. And this equals minus qb over m vx. And you'll notice that this is just minus omega. And we know that Vx equals alpha cos omega t plus phi. And we can integrate this with respect to time to get Vy rather than V dot y. And this, the omega comes out the front and cancels with the omega that is already there. And we get our general solution for Vy, which is minus alpha sine omega t plus phi plus a constant. So here we have our general solutions for Vx, Vy, and Vz. Vz is just 0. And we also have our formula for omega. But there are a lot of constants here that we don't know. We don't know what alpha is, we don't know what phi is, and we don't know what c is. And we can find some of these by looking at our first equation from earlier. And if we manipulate this, we can get an expression for v dot x. So first thing we do is we divide m through the equation. And we notice that in front of the Vy, we have qb over m, which is exactly the same as omega. So we can put omega in. And we can also substitute in Vy for minus alpha sine omega t plus phi plus c as above. And just tidying that up a little bit, putting the omega into the bracket and splitting our equation so that we have some constants at the front and our sine function at the end. Now, another way that we can get to v dot x is by simply taking vx equals alpha cos omega t plus phi and taking the time derivative of it. And we can write this as v dot x equals 0 minus omega alpha sine omega t plus phi. And it makes it very clear that our bunch of constants at the front for our v dot x earlier is just 0. And we can rearrange this to get C equals minus QE over omega m. But if we rearrange our omega, as you can see above here, we get B equals omega m over Q, which is almost what we have at the bottom. And rearranging, we get C equals minus E over B. So we found C, it is minus E over B, but we still don't know what alpha or phi is. And in order to find these, we will look at the boundary conditions. Now we know that at time 0, the velocity in all directions is 0, as it is given to us in the question. And so we can say that Vx equals 0 at time equals 0. Now we've just subbed in t equals 0 into this equation, and we can rearrange to get alpha cos phi, and phi has to equal pi over 2, as that is when cos equals 0. So we found phi, and we can use this phi to find alpha. By substituting it into our expression for Vy, we can get 0 equals minus alpha sine pi over 2 minus E over B. And sine pi over 2 just equals 1. So we get 0 equals minus alpha equals minus E over B. And so we have our solution for alpha. That's fantastic. So now that we have our constants, omega, c, alpha, and phi, we need to find our position vectors, rt. And we have our components for our velocity vectors. These in the x direction is minus e over b cos omega t plus pi over 2, which we can simplify as e over b sine omega t. And we also have Vy equals minus e over b sine omega t plus pi over 2 minus e over b, which we can simplify as this, and simplify again as e over b cos omega t minus 1, and our Vz is simply 0. So if we get rid of all this ugly work and then just have the bits at the end, in order for us to find our position vectors, rt, we need to integrate each of these parts. So our position vector in our x direction is the integral of our velocity component in the x direction, same for the y and same for the z. Now, solving these is not too difficult. We simply take, for this first one, we change the sine into a minus cos and take the omega out to the front, and on our and add a constant. For our second one, we change our cos into a sine and have the omega come divided out the front, and our 1 becomes t, and we have a constant c. And for our z component, it is simply a constant. So here are our equations for our position vectors in x, y, and z. Now, once again, we have a couple constants that we need to work out, but we can just use boundary conditions as before. As we know, at time equals 0, our position function was also 0. So if we sub in t equals 0 into our Rx equation, we get our cos turning to 1, and since the entire expression equals 0, we can deduce that C1 equals 1 over omega E over B. For our y, we again sub in t equals 0, but since sine 0 equals 0, this part of our expression goes away, and anything times by 0 also equals 0, and this goes away. But since this entire expression equals 0, C2 has to equal 0. So C2 equals 0. And for our z, it is very simple, C3 equals 0. So these are our constants for our x, y, and z components of our position function. Now, the one final thing that we have to do in order to get our final answer is we substitute our C1, our C2, and our C3 into our expressions for our x, our y, and our z. And this is it for our x. for our y and for our z. Now, one little thing we can touch up is we can take a factor of minus 1 over omega times e over b out of our x expression, which leaves it like this. And this is our final answer. I'd like to thank you all very much for sticking with me to the end of this question. I know it was a bit of a nasty monster question. But if you have noticed any errors that I've made during this solution, please do let me know. But yeah, thank you very much for watching.